we propose a domain-invariant learning approach for image classification. This is the joint work with my co-authors, Alan, Heejong, and Mert. First, let's look at the problem setup and the motivations behind our approach. We consider the anti-causal learning setup, whereby we need to predict a label y given the input x and z. The setup is anti-causal because the output y is the cause of the input x. An example task could be predicting whether a patient has skin cancer or not, given his image. In this case, x is the image and y is a binary indicator variable for melanoma. The confounder z is a variable that influences x and may be spuriously correlated with y. For this example, z can be the lighting condition. In domain-invariant learning, there are multiple sites with different data generating mechanisms. This figure shows 6 different sites with different mechanisms. However, the mechanisms that generate x and from y and z is assumed to be stable across sites. The common setup is to assume there are 2 sites. In the first site, E1, there exists strong spurious correlation between y and z. Data from this site is used for training. In the second site, E2, there's no correlation between y and z. Data from this site are used as test data. However, there could be other possibilities such as E3, E4, or E5. Given the multitude of data generating mechanisms, it is important that invariant learning approaches should be able to deal with different mechanisms. This motivates us to come up with an approach that works with multiple confounders, since there can be multiple, works with different types of causal relationship between x, y, and z. For example, y can be the cause of z or vice versa. And it should work with a multiple training site or a single training site. One insight that we found is that the conditional prevalence can be estimated easily in many applications. We can leverage this for domain-invariant learning. Next, we'll formulate the way to adapt to different domains or different sites using conditional prevalence. We name our approach CoPA. We start with a stable generation assumption. This is a generative distribution, so we use Bayes' rule to invert it. We can predict the label of y of a new sample at the site, EJ, by taking the argmax of the predictive distribution. By dropping some terms, we can obtain a simplified equation. And then by observing that the ratio Rxz is invariant across sites, we can learn this ratio using a neural model f theta with parameters theta, using data coming from multiple sites. The conditional prevalence adapted predictor uses the same f theta but different conditional prevalence. This outlines the architecture of CoPA. One attractive point of CoPA is that it can exploit pre-trained models as the backbone. We evaluate CoPA in several experiments using various real and synthetic datasets. One experiment uses the skin cancer datasets from Isaac. There are multiple training sites in this dataset. Notice the prevalence varies drastically between sites. Another experiment uses the chest X-ray datasets from 3 different hospitals. The training data comes from one site in this experiment. For the 2 experiments with real data, there are multiple confounders Z. Most confounder variables are discrete, with the exception of age. Since some causal relationship between Y and Z are unclear, they are left unspecified, and CoPA is not affected by this. For the skin cancer classifications, we can see that CoPA obtains the highest F1 score compared to the other models across both test sets. Similarly, we observe the same trend for the chest X-ray experiment, whereby again, CoPA outperformed the baseline models. In short, in this work, we propose CoPA, a domain-invariant learning method. CoPA consistently outperforms baselines in multiple experiments with real data. Please refer to our paper for more experiments and applications. Thank you for listening.